All right, guys, so in this video, we're going to look at some practice problems from Chapter 5. And at the end of the video, I'm going to list some of the more important equations just so you have them all in one place, all right? So in the first problem, we're going to look at total energy. So it says two gases are confined to a cylinder piston system. And I'm going to switch my pen color here real quick to blue. There we go. Where gas A and B react to form solid C. So right off the bat, I know I have A as a gas plus B as a gas yields C as a solid. As the reaction occurs, the system loses 1150 joules of heat, and the piston drops as the solid is formed. Okay, so we have a piston system, and in a piston system, wow, that was terrible. So we have a piston, and it's laying on top of the cylinder, like that. Let's draw this a little more accurately here. There we go. All right. So the only thing pressing on the cylinder, okay, is the atmosphere, because we're not in a vacuum. And so as A and B react and form the solid takes up less volume than the two gases, and so we would expect our piston to drop. So it's going to drop down lower. All right. As the piston drops and the volume decreases under the pressure of the atmosphere, it does 480 joules of work on the system. What's the change in internal energy? All right, so we're looking for the change in internal energy. So that's delta E. And we know that that is Q plus W. All right, we're given both Q and W in this problem. We don't really have to hunt for it. So Q is negative 1150 joules. Now, why do I know it's negative? Well, it says that the system is losing heat energy. And then we have the work, which is being done on the system. So since work is being done on the system, we know it's positive. So that's 480 joules. All right, so delta E is just Q plus W. So delta E equals negative 1150 joules plus 480 joules. My units are good here. I don't need to convert anything. That is something to look out for. All right, make sure that you don't have like joules and kilojoules that gives you. And so add those two things together, and I get delta E is negative 670 joules. So there's my energy. That would be a change in energy or total energy problem. All right, in problem 2, we're going to look at two different versions of a similar problem. Both of these enthalpy change problems we solve with the factor label setup, the dimensional analysis stuff that we've done, the brackets, right? So the first question says, how much heat is released when 4.5 grams of methane gas, CH4 gas, right? We should know methane at this point, is burned at constant pressure, given that the delta H for the combustion of methane is negative 890 kilojoules per mole. All right, now hopefully at this point in chemistry, you're starting to recognize that if a problem gives you grams and moles, you can convert. And so in this case, I have two brackets that I need to use to set up. So I'm going to say 4.50 grams of CH4. I'm going to convert grams of CH4, so that's roughly 16 grams of CH4 to a mole of CH4. Now I've got moles on top. Remember, moles can go to like anything. So 1 mole is equivalent to negative 890 kilojoules as far as the delta H of combustion is concerned for methane. So this gets rid of grams. It gets rid of moles. I'm left with kilojoules, and that's what I'm after. So 4.5 divided by 16 times negative 890 gives us negative 250 kilojoules. And there's my answer. right? So that would be delta H. Now, something you might be asked about this, is this reaction endothermic or exothermic? Well, it's negative, so that tells us it is exothermic. All right. In the second one, we have, using the following reaction, calculate Q when 5 grams of hydrogen peroxide, again, H2O2, something we should probably know at this point, decomposes at constant pressure. All right. Well, I'm still going to do a bracket setup. I'm still going to go grams to moles, right? I have grams. I need to get to moles, all right? And so this delta H here, right, it is implied that that is kilojoules per mole. So let's set it up. We have 5.00 grams of H2O2. Right, and we're going to convert grams of H2O2, which is 34.01 grams of H2O2, to a mole of H2O2. Now this is where this is going to get interesting. In the problem, I have 2 moles of hydrogen peroxide. So in the first one, in the first setup we did, we had 1 mole, all right? But in the second one, we have to do 2 moles, okay? Because in this specific instance where it's giving us a delta H for a reaction, it is taking into account the fact that that's a 2. And so I'm going to put 2 moles on the bottom and negative 196 kilojoules on top. And so now I'm going to run my math problem, right? 5 divided by 34 divided by 2 times negative 196. And I'm going to get 14.4 kilojoules as my answer. All right, this is positive, so we would probably say endothermic if we were asked about the state of the reaction. So those are pretty simple, all right? Once you've seen how to set them up, you're like, oh, okay, this is not as big a deal, all right? So those are our enthalpy change problems. Just make sure that if you're given a setup like the second one, that you account for balanced coefficients. So this is our balanced coefficient. All right. The third question is going to be a Hess's law problem. Now, Hess's law can be a little bit daunting, but it's really not that big a deal, okay? So the question says, the enthalpy of combustion of carbon to carbon dioxide is negative 393.5 kilojoules per mole, while the enthalpy of combustion for carbon monoxide to carbon dioxide is negative 283 kilojoules per mole. Find the enthalpy of combustion for carbon to CO. So this is what they've given us, all right? Carbon as a solid to O2 plus O2, right? Because it says combustion to get CO2. So this is number 1 is negative 393.5. The enthalpy of combustion, again, for O2 of carbon monoxide to CO2, right? Here's number 2 is negative 283. So I have these two things. Hess's law says that we can take a reaction in small steps and figure out the total enthalpy of a change. What that also means is if you know just random small steps, you can find the enthalpy for any other setup. So in this case, I'm trying to get to this. All right, I want to know carbon that combusted to give me carbon monoxide. So carbon combusted, right? I have oxygen to get carbon monoxide. Now, before we go any further, look at this 1/2 I had to put in there. Why did I have to put that in there? Well, I can't change the carbon monoxide or the CO2 because that's what it gave me right here. So the combustion has to account for that to make sure that the number of oxygens is right. Now, obviously, you can't combust a half of an O2 molecule, but on paper, right, in theory, we absolutely can. So this 1/2 is an okay thing to see. Same thing down here, right? I just have 1 oxygen in my product, so I only need 1 of these there, so half of 2 is 1. So you may have to drop halves in when you do combustions. Look for that, all right? It's something you might see. So here's the question. How do I take 1 and 2 and rearrange this to get 3? Well, the problem that I see here is I have CO2 on both sides, and this is no CO2 on number 3. So I have to cancel out the CO2. So how do I do that? Well, I'm going to flip this second reaction, and I'm going to make it CO2 as a gas decomposes, right, breaks down, uncombusts, which obviously we know is not true, but in theory, right, the math tells us if it's negative going one way, it'll be positive going the other to give us CO plus 1/2 O2, where delta H is now negative delta H, so that's going to be 283 kilojoules. So anytime you flip a reaction, you have to flip the sign on delta H. Now, I'm going to leave number 1 the same. So carbon plus O2 yields CO2 with a delta H of negative 393.5 kilojoules. Let me switch over to red. Or green. We'll do green, apparently. All right, so what cancels out here? Well, I have CO2 on the top on the right side of the arrow. I have CO2 on the bottom on the left side of the arrow. And so that's great, right? That's canceling out two things that I don't need. Well, what about the other thing? Well, we have this third equation, C plus 1/2 O2 yields CO. Well, look at there. Now we can cancel out our 1/2 O2s because they're on both sides of the equation. So this is going to leave me, okay, with an overall reaction, all right, that I can write, which if I can get my pen color here, there we go, is going to be C plus O2 from right there is going to yield CO. And with that, obviously this has to be a 1/2 in order to balance to make it happy. And so since I added these two things together, I can just add these two delta H's. And so when I do that, I'm going to get negative 393.5 plus 283. And that's going to give me negative 110.5 kilojoules equals the delta H of that reaction. Now we can do kind of a logic test here. If I'm combusting something, do I expect that to be endothermic or exothermic? Well, I probably expect it to be exothermic, and I do in fact have a negative sign out front, and so that's a good indication that we're on the right track. But all I did was just flip my second equation in order to give me my final equation. Easy stuff, all right? So looking at chapter 5 as a whole, these are the big equations that you need to know. Now, a couple in here I didn't work, right? I did work this one. I just now did one of those, okay? And we actually ended up looking at enthalpy change at constant pressure, but we did it with our brackets, which is the easier way to do it. But this is the equation that you need. Now, specific heat is from year 1 chemistry, so hopefully you remember that from last year. Specific heat's not really all that difficult. And these two are also pretty simple. This one you will likely not see on the AP test or anywhere other than conceptually speaking. But in case you needed it, here it is, okay? So if you have questions, let me know. I'll be glad to help you guys out. And that's about it for practice problems from chapter 5.